Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Today we are going to discuss synthesis of aromatic compounds, SNAR, nucleophilic aromatic substitutions. Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. So today we are going to discuss the chapter Order of Events for Retrosynthesis. This is lecture number 5. As far as this chapter is concerned, the chapter is about the order of events for retrosynthesis. So there will be some guidelines in whole of the lecture which we must take care when we are doing the retrosynthesis. So the contents contain guideline number 1, guideline number 2, guideline 3, guideline 4, similarly guideline 5, and then there will be some guideline 6. So these 6 major guidelines will be discussed for the order of events in the retrosynthesis. Guideline number 1. First, consider the effect of each functional group on the others. We shall have to consider that what effect the functional groups are creating on each other. How are they affecting each other? For example, if there are 2, 3, 4 substituents on the aromatic ring, so we shall be considering the effect of all of those on each other. Number 2, add first, that is disconnect last. There is a sequence of disconnections. There is the first disconnection, then synthones, then those synthones will be disconnected, the new synthones will be formed. So first you are going to add or synthesize, do the synthesis of those synthones which you have disconnected at the last. As you are having a product, imaginary product, you are doing disconnection. First disconnection gives some products or synthones, actually we should say. Then those synthones will be disconnected to make some simpler synthones. The synthone which is achieved at the last disconnection, that will be the first synthesis of the series, and the one that will increase the reactivity in a helpful way. So we shall have to add that one substituent firstly, that will be increasing the reactivity, so that there is a step of reactions after the first synthesis, first addition, first reaction. So we should be adding that substituent first, that will increase the reactivity, so that will be helpful for further series. So for the aromatic compounds, introduce first that group that helps by reactivity or direction the introduction of others. Now suppose we are adding a group into the aromatic system. First look at the product, how many groups are there. So first check which one would be added first, then which one will be added at the first, and then you will see that what is the effect of this one on the others when we shall add, like someone is at odd position to one another. Is it ortho directing, meta directing, para directing? So all these things should be kept in the mind, that you shall be thinking, you shall be considering their reactivity, orientation, all the things before adding the group. Point number 4, the analysis of the perfumery compound 1 could be tackled by two possible first disconnections. You can look at the disconnections at the bottom of the slide. Friedel-Crafts alkylation A would reasonably well with the secondary alkyl halide 2, but the ketone in 3 is meta-directing and would give the wrong product. Like in disconnection A, we are having two syntones, secondary alkyl halide 2 and ketone, which is number 3. If you are getting secondary alkyl halide, then it is fine. It will be added up. We shall be adding that up into the aromatic ring 3. We can get this substitution or substituent, but as we cannot get, if we are adding up 3 and we are alkylating 3 with 2, so that keto group will not give the orthopara direct, it will give meta direct. It is meta directing, it will give product at the meta position, so wrong product will be there. So from 3 we cannot get this product. Friedel-Crafts acylation B would give the right product, as the alkyl group in 4 is orthopara directing. Further, the alkyl group in 4 is activating while the ketone 3 is deactivating. Now there are two advantages of the B disconnection, that will be the synthesis will be Friedel-Crafts acylation of 4 and 5. Now if you are disconnecting like that, you are getting one part of the disconnection as 4, one synthon, and the other one as 5. So this is a good approach. Like 4, when will be acylated, we can get 1 easily. And number 2 is that if we would use 3 and then alkylate, first one product will not be found because 3 is containing ketone is orthopara directing. And second one is that this is deactivating ketone while alkylated benzene or alkyl group is activating. So B disconnection is preferred in all respects. Now here next example, what is over there in this slide also, that is emphasizing the first aspect of guideline number 1. Now the guideline we are discussing, the first point which we have discussed about the functional groups, effect of functional groups on each other, we must be considering the point. Some functional groups are so deactivating that it is difficult to do any further chemistry once they have been inserted. In other contexts, it may be that they are so unstable that would wish to risk any further reactions. Musk Ambert 6 is a synthetic musk. You can see at the bottom there is a disconnection in which the first one compound written as number 6, Musk Ambert. Now it is essential in perfumes to enhance and retain the fragrance. It has 5 substituents around a benzene ring. 2 of these are the nitro groups and they are deactivating, so that we want to add them at the last. So we will disconnect them the first. Those who are being disconnected the first will be added at the last. So the rule, first disconnection will be added at the last. So disconnect nitro, because it is deactivating, it should not be added the first, it should be added at the last. So disconnect them first. So we have disconnected them and the result is compound number 7. Now the compound number 7 is having 2 possible disconnections, disconnection A and B. One point that from disconnections of 6 we got 7, and we have broken down or we have disconnect carbon to nitrogen bond, and by nitration we can generate that carbon to nitrogen bond. So compound number 7 can be having two disconnections. One can suggest synthone 8 and one can suggest synthone 9. So now if you check, if you are disconnecting you are doing B disconnection, you will be getting 8, and when you are doing A disconnection, you will be getting 9. So let's see on the next slide what is discussed about this. Compound 6, after disconnection of nitro group, we got compound 7. 7 has two possible disconnections. One will give 8 if we do the B disconnection, and if we do A disconnection, then we shall get 9. Now the synthesis for the compound is clarifying the scene. The synthesis is straightforward and providing we alkylate first and acylate second. The reason is that we need both the substituents at para positions, so we must have to add first that one substituent which shall be orthopara directing. Of course, the orthopara directing is here in both of these alkyl group and acyl group. The orthopara directing is alkyl group. So we shall be when we shall disconnect this compound, we shall disconnect. The first disconnection will be added at the last. So first we shall disconnect what? First we shall disconnect acyl group and then alkyl group. So we shall start from benzene, come back to the synthesis. We shall start from benzene. We shall do a Friedel-Crafts alkylation using alkyl halide. Which alkyl halide will be used? Secondary alkyl halide will be used here, and using aluminum chloride we can get product 4, and then by the Friedel-Crafts acylation in the presence of aluminum chloride we can get compound number 1, that is will be giving 86% yield. So the branched alkyl group in 4 ensures that the para ketone 1 will be the main product by steric hindrance, and of course we know that alkyl groups are the para directing, but here due to the steric hindrance, because it is a bulky group, para product will be the major product. So 86% yield will be of the para product. Now next we could disconnect either methyl group 7A or the butyl group 7B with Friedel-Crafts alkylation in mind. Now just for the reference I have put smaller one disconnection which we have done on the previous slides. Just for your reference I have pasted it over here. Now you can see that we can do 7A disconnection or we can do 7B disconnection. There are many reasons for choosing 7B. Why we are choosing 7B? The methoxy group and the alkyl group in 8 and 9 are ortho-para directing. After the disconnections we are getting 8 and 9. Now the methoxy group which is present in 8 and 9 both, they are ortho-para directing, but the methoxy group wins because it has lone pair of electron on oxygen, and that is localized into the aromatic ring, that is electron donating resonance effect. So 9 will give the wrong product but 8 will give the right product. So if it's considered, look at this mini disconnection I have shown on the slide. There is 9. So 9, when we choose the 9, but the 9 will give, like if you are going to make 7 from 9 by Friedel-Crafts alkylation, that will be giving ortho-para product. So we cannot get 7 from 9, but 8 will give the right product. If we are doing Friedel-Crafts alkylation on 8 with tertiary alkyl halide, then we can get easily 7. So in addition, alkylation works well with tertiary-butyl SN1 mechanism but badly with the methyl group. In the case of A8, if we are choosing disconnection A and we are getting 9, in that case 9, we shall have to proceed 9 for making up 7. But in case of disconnection B, we are getting synthone 8 and we shall have to convert 8 into 7. So in that case, when we are choosing 8, we are doing alkylation, and we are doing alkylation with tertiary butyl halide. Sorry, I did use the word tertiary butyl halide, so it's alright. So tertiary butyl group, when we are using tertiary butyl group, tertiary butyl halide, SN1 mechanism will move on, and that is very good. Like in the SN1 mechanism, it is a two-step mechanism. SN1 means two-step mechanism. Rate determining is only one molecule in the rate determination. So that is the first one, and so that's the first step in the rate determination is the rate determination step, and in that step, tertiary butyl will becoming a cation, and the removal of halide will be over there. So the most stable cation is the tertiary cation. So tertiary cation will be formed, SN1 mechanism will proceed. But in the case of 9, if we convert 9 into 7, we shall have to use methyl halide. And when we are going to produce 7, methyl halide will be not very prompt by SN1 mechanism. As you know that for SN1 mechanism, the most stable cation is favored. So tertiary butyl group, which is used for the conversion of 8 to 7, will be a good choice. Our starting material 8 is the methyl ether of available metacresol 10. So is easily made by methylation of the phenol. So there is an option that from where can we get this 8. So our starting material 8 is basically is the methyl ether of available metacresol. For example, there is the metacresol, you can see at disconnections or disconnections, you can say that down 10 to 8 and then to 7 and then to TM6. This is not disconnection, basically this is synthesis. So now it is now going on synthesis. We are going back from synthone 10 to 8 and then 8 to 7 and then 7 to the target molecule. So our starting material 8 is the methyl ether of available metacresol. There is a metacresol, like at point 10 you are looking at the structure 10, there is a metacresol, then base is acting on the metacresol, and methylation is done of this phenol. So methyl is added over there, so 8 is formed. After that 8 is converted into 7 by simply Friedel-Crafts acylation, then Friedel-Crafts alkylation, and then 7 will be converted by nitration into the target molecule, which you can see in the smaller one diagram, having 2 nitro groups, which will be, if we are making them from 7, they will be at ortho and para position to the. Now as we have seen in the rules of orientation, that if there is ortho para directing groups and they are competing each other, that who is the most stronger will be orienting the incoming electrophile. So here methoxy is the strongest or the para directing group, so it will direct the incoming nucleophile. So the nitration will be done at ortho to methoxy and para to methoxy. So we shall be getting the product 2 nitro, ortho and para to methoxy, and other substituents which we have made over here. Now we are going to do guideline number 2. Changing one functional group into other may alter the reactivity dramatically. So I have introduced FGI to you, and you have studied in the first chapter also. So changing one functional group to the other may alter the reactivity, and that is dramatic change in the reactivity. So changing an alcohol or phenol to a tertiary butyl ether increase the steric hindrance. So as you have seen in the previous slide, we were uh, changing alcohol or phenol into tertiary butyl ether. We have not changed it into tertiary butyl ether, but if you want to change that alcohol or phenol, replacing that hydrogen with tertiary butyl, it will increase the steric hindrance. So alcohols and aldehydes or ketones are easily interconverted by redox reaction. So we can convert alcohol into aldehyde by simply oxidation, and secondary alcohols into ketones, and they can be easily converted, and by only doing the redox reactions, oxidations. By oxidations, alcohols can be converted into aldehyde ketones. By reductions, aldehyde ketones can be converted into alcohols. The carbonyl compounds are electron withdrawing, while alcohol is weakly electron donating. As you know that if we are considering alcohol, that is electron donating, but the carbonyl compounds are electron withdrawing. So there is a difference in the reactivity. There is a difference in the orientation also. Both aldehyde and ketones or carboxylic acids are deactivating. Carbonyl compounds are most of the times deactivating. They are electron withdrawing. They are orienting to the meta position, while alcohols are orienting to the ortho para positions and electron donating. Most dramatically of aromatic compounds, the nitro group is powerfully electron withdrawing, deactivating meta directing, while amino group, which is made by the reduction of nitro group, is strongly electron withdrawing, activating ortho para directing. So this is just like a twist change, like a U-turn. So like if we see there is a nitro group, we just do the reduction, we convert into the amino group. Nitro is electron withdrawing, is deactivating, meta directing, while amino is electron donating, activating, ortho para directing. So in analysis featuring FGI, it may pay to consider at which stage to carry out some other reactions. So in FGI we shall have to see that at which stage we have to convert the functional group. A simple example is the tetrachlorocompound 11 that is clearly made from the toluene by some forms of chlorination. Now there is 11, you can see here 11 is a tetrachlorocompound, 3 chloro in along with the methyl and 1 chloro directly on the aromatic ring. In fact, we must change the meta directing trichloro compound, trichloro substituent group into ortho para directing methyl group before we disconnect the aromatic Cl bond. Now just first of all do the FGI. We should disconnect CCl bond, and that will be produced by the chlorination. If we disconnect the CCl bond, we have got synthone 12, which is having a CH3. So we have disconnected this CCl3 bond. There are 3 CCl3 bonds. We shall be making them simultaneously from chlorination. Then we have to disconnect that chlorine which is directly attached with the aromatic ring. So by the C to Cl disconnection, and again this will be obtained by the chlorination, we have got synthone toluene. So from 11 CCl disconnection, FGI or CCl disconnection both, we got 12, and from 12 we got toluene. So in fact that I have already told you that there will be now options. CCl3 is a matter directing group, and these both substituents are attached at para to each other. So we shall have to see how can we synthesize it, which substituent should come before. The compound was actually used to make trifluoro compound. This compound which I've shown trichloro compound is actually used to make trifluoro compound. So the chlorination of toluene with Lewis acid will give 12, and the chlorine and PCl5 does the probably radical chlorination of the methyl group to give 11, and then the fluorination will be done to produce 13. Now you can see the sequence down. Toluene by the Friedel-Crafts alkylation has been converted into chloro toluene, and then by chlorination of in the presence of PCl5 we got the chlorination of this methyl which is attached on the aromatic ring, the methyl of toluene. So we have converted the CH3 into CCl3. From 12 we have obtained 11. The yield was 93%. Using PCl5 we have chlorinated this methyl attached to the aromatic ring, and then we have just do the fluorination in the presence of stibbium pentafluoride. We have converted this CCl3 into CF3, and 95% yield we got in the product number 13. Now some substituents are difficult to add, so it is best to start with them already present. There is a difficulty in some substitutions, so it is necessary to start with all synthesis of aromatic compound with benzene. It is not necessary that we should start with benzene. At a glance at any supplier's catalogs will show the great range of aromatic compounds available. So we should actually start with the already present, commercially available, commercially cheap materials. So the chief example of substituents are phenols, and the ethers they are derived from them, as there is no simple reagent for electrophilic oxygen. So these are phenols and ethers are commercially available because there is no simple reagent for the electrophilic oxygen is available which can make phenols and ethers. So commercially available phenols and ethers are used, but a methyl group and a primary alkyl group in general are also difficult to add, as Friedel-Crafts alkylations with primary alkyl halide lead to rearrangement products. Similarly, we see that if we are having a methyl group and a primary alkyl group, in general when we do the Friedel-Crafts alkylations with primary alkyl halide, that is leading to the rearranged products. So again we shall think about the commercially available reagents. The tri-substituted benzene 14 was used by Woodward as a starting material for his synthesis of the natural product reserpine. When he was synthesizing reserpine, he did use starting material compound number 14. It too has to be made. We shall not add the methoxy group but bi-anisole methoxybenzene as starting material. So both nitrogens will be added by nitration, but in which order? Now we can check that now. This is command number 14. This is used for the natural, Woodward is used for the synthesis of natural product reserpine. So there can be like first one compound, rather than using benzene, methoxybenzene or anisole, which is called anisole. So anisole is used, already commercially available prepared anisole is used for the synthesis of this compound 14, and then after that nitration of anisole is done, and how that nitration is done, that is also managed. So the NH2 group which is being seen over here, that can be obtained by the reduction of the nitro group into imino group. Now the methoxy group is ortho-para-directing. So nitration of anisole 15 will give mostly the para product 16 due to steric hindrance. Methoxy is having three protons, so although products, although nitration is not very much preferred because of the steric hindrance, the major product is the para nitro. So nitric acid is alone is needed. A mixture of nitric acid and sulfuric acid gives 2,4 dinitroanisole as methoxy group is activating. So what is happening? 2,4-dinitroanisole is produced in the case if we use mixture of nitric acid and sulfuric acid. Now this also shows that a second nitro group cannot be introduced in the right place from 16. Now there is a second nitro group which must be added at position meta to methoxy. So this shows that there is not the right way to make to introduce two nitro groups at the same place. So first so what is done then? Reduction of the 17, the reduction of the amine 17. Many reagents could be used, but titanium tritanium 3 oxidation state gives good results, gives a more powerful activating group that might direct the nitration to the right position. Now if we cannot have by the nitro group we cannot get here the nitro group at the position to the this one nitro, so we can reduce this nitro into amino will be an activating, then we do the nitration, and then we shall get the nitro at ortho to amino, and para is already occupied, and we shall get ortho to amino nitro group, then we can get the product. In practice, there is too much activation in 17, and attempted nitration oxidize the molecule. Because it is too much activating NH2, so when nitration was tried, it oxidized the molecule. Instead of nitration, oxidation was taken place because NH2 is too much activating. The amine must be acylated first. As we have seen, we are seeing here from 17, it is being converted into 18 after acylation. So amine must be acylated first, and then without oscillation of 18 can be nitrated, nitric acid alone, to give 19. So then the same product 18 without separation from 17, we can add nitric acid only to this one to get 19 from this mixture. Hydrolysis of amide gives 14 in excellent yield. So when amide is, we need back NH2 amino group, we just do the hydrolysis of this 19, so we shall get back the amino group, and amide will be hydrolyzed, producing the product that is 14. So on the whole, we have done what? We have done the acylation of 17 here, and after acylation we have done the acylation with the help of acetic anhydride and acetic acid, and in the presence of water, and then we have done the nitration of 18. We got 80 nitro group on ortho, and para is occupied ortho position, ortho of NH2 group. NH2, as I have discussed it before, the more powerful ortho-para-directing will orient in case of two ortho-para-directing are competing with each other. So in NH2 or NHAC substituted amine and methoxy are competing with each other for directing the nitro group. So the nitro will be basically directed by amino group. So ortho to the amino will be the nitro substituted, but we can separate from here the desired one on which ortho we want the product. So we want on 19. So from the hydrolysis of this acylated amine 19, we can get by the hydrolysis we can get back the product 14, which is the target molecule. Some dye-substituted compounds are also readily available and they may contain a relationship, especially although that is difficult to achieve by electrophilic substitution. Hence, as a selection, a supplier's catalog will reveal more. So here are some examples of dye-substituted compounds. They're very difficult to prepare. Electrophilic substitution, which is applied for preparation of the compounds, is a bit difficult. So we must have a selection of the supplier's catalog. Like there is a salicylic acid. This is containing carboxylic acid hydroxyl group, and anthranilic acid, carboxylic acid, and amino group ortho to each other, phthalic anhydride containing two carboxylic groups, this is an anhydride, and mesitylene having 3 methyl at positions meta to each other, and ortho catechol, meta resorcinol, para quinol, or two hydroxy groups. If are ortho, then it is catechol, resorcinol at meta position hydroxy groups, and when two hydroxy at para position, it is quinol. Then the cresols having hydroxy and methyl group, ortho meta para cresols. And then as the diphenyl, which is having two aromatic rings joined to each other by a bond. There is a bond in between two phenyls that is called diphenyl. One carbon of one aromatic ring and the other carbon of the other aromatic ring are making up a bond with each other. Now, an example is 21, that is the target molecule, and it is needed for the synthesis of GSK anti-asthma drug salbutamol. So it is used for the synthesis of salbutamol, which is structure number 20. You can see the very first structure in the slide. So this ketone, that is 21, could be made by a Friedel-Crafts acylation of 22. The compound 22, which is actually a salicylic acid, that Friedel-Crafts acylation of salicylic acid we shall just do, and we shall make up the compound 21, the ketone 21, which is necessary for the formation of salbutamol, which turns out to be a salicylic acid, and with acetyl chloride we do the Friedel-Crafts acylation of structure 22 salicylic acid. So you can see, just if we do the disconnection, we shall be first disconnection will produce synthone 21, then Friedel-Crafts acylation of there have been shown that there are many there are two arrowheads, one the upper one, the lower one. It is showing there are many steps in between from 21 to 20. So we are discussing right now 21. So we can do the disconnection of 21 to 22 by C to C disconnection of this carbon to oxygen, the group which is the keto group. We can disconnect this carbon from the carbon of aromatic ring, then we shall be synthesizing it by Friedel-Crafts acylation of salicylic acid, which is 22. The first synthone, by the disconnection of 21, we got 22 salicylic acid, and the other synthone is acetyl chloride. Now this synthesis is easier than it may seem, as the free phenol, rather than interfering, can be acylated to give the ester 23, which rearranges aluminum chloride to give 21 directly. Now we are saying that the synthesis is easier than it may seem, as the free phenol, like if you can see on the structure 21 there would be a free phenol, so we shall be doing the acylation of the phenol, and we shall be getting product 23. Look at the downward synthesis, you can get my point better. Even the intermediate 23 is available and quite cheap. It is aspirin. Like we are if we go through this approach, like we are having salicylic acid, we can acylate the salicylic acid, we can get aspirin, and then we can do the Friedel-Crafts acylation of this 23 aspirin, and we shall get then the acyl group which we shall be having on the target molecule if we go towards the synthesis. So this is an easier synthesis. So but there is a problem that if there will be free phenol in the salicylic acid and we do the Friedel-Crafts acylation, then free phenol OH will be interfering. So we can do what? We can do first protection of this phenol with the help of acetic anhydride that will be protected, and then Friedel-Crafts acylation will be done, and the compound target molecule 21 will be formed. Now, some groups can be added to the ring nucleophilic by nucleophilic substitution. So before that we were discussing the electrophilic substitution. Now some groups can be added by the nucleophilic substitution. This is mechanistically more difficult than electrophilic substitution, and this requires an electron withdrawing activating group such as nitro or carbonyl, ortho or para to their normal leaving group such as a halide. There are conditions in nucleophilic substitution. So in electrophilic substitution we do not have those conditions. What conditions are needed in the nucleophilic substitution? We need electron withdrawing groups, which should be ortho or para to the leaving group, which is normally halide group. So fortunately, nitration of Friedel-Crafts acylation of halo compounds was the activating group in the right position of nucleophilic substitution. Now, if we are doing the nitration of Friedel-Crafts acylation of the halo groups, then what are we getting? Like this is halogen is actually electron is activating group, and it is ortho para directing also. So the halo is activating, so that can put the incoming nucleophile at ortho or para position. So Friedel-Crafts acylation of fluorobenzene 24 gives the ketone 25, and displacement of fluoride by the addition elimination mechanism gives amine 26. So we are doing the Friedel-Crafts acylation of fluorobenzene here 24. After the Friedel-Crafts acylation, acyl group will be substituted, and that will be at the para position, and then we shall treat it with alkylamine, so that this fluoro will be substituted by alkylamine. So what is going on over here? It does mean that we need to add some of the substituents to the ring with the help of nucleophilic substitution. So for the nucleophilic substitution, first we need some electron withdrawing group attached to the ring, and then we need some electron withdrawing, but that would be the activating such as nitro, carbon, ortho and para to the normal leaving group as halide. So in this example we have seen the implementation of this point. If this kind of activation is not available, nitrogen cannot be displaced from diazonium salts by SN1 mechanism. Like you see the disconnections down from, like the acid 27 was needed at Hull University in work on liquid crystals. This is the target molecule, the acid 727. The skeleton is diphenyl, which reacts in para positions with electrophiles. So this is a diphenyl, and the reaction of this diphenyl takes place. It reacts at para positions. Any electrophile which will come will react at para position. So the chlorination is difficult, therefore, and we need to replace the hydroxyl group with a group with more electron donating than the phenyl ring. So enamine is the answer, 28, and that soon takes us back to the diphenyl. So we are doing first of all FGI. We are converting that. First of all, we are doing FGI. We're converting this carboxylic acid group into in the synthone, we are converting it into the NH2 group, because the NH2 group can, with the NH2 group there can be halogenation in the right direction. Because if there would be a carboxylic group, we cannot get chloro at ortho position to the carboxylic group. So from 27 we can get 28 by FGI and synthone. Then we can do the disconnection and we can connect the C to chloro bond, and we shall get 29 simple amino substituted diphenyl. Then we shall do FGI and we shall get nitro group over here, because we can make it very easily. Nitro group, we can convert very easily nitro to amino. So we do FGI, functional group interconversion, we get 30, and then we shall just do the disconnection of C to N1 and we shall get diphenyl as a synthone. So what have we done? So in this slide we have said that if we are having 27, we need 27, that's the target molecule. We shall first do the first do the FGI. We shall have NH2 instead of COOH, and we shall be having chloro substituted. Then we should do first disconnection of C to Cl bond. Then we shall do again FGI. We shall be we cannot have NH2 direct from here from diphenyl, so we must have to do the nitration, and then we shall be getting the reduction of nitro diphenyl. So we shall start from diphenyl from 30. The synthone by the disconnection we shall get will be the C to N disconnection, and diphenyl we shall start the synthesis. Now the nucleophile to introduce the COOH group is cyanide. Cyanide ion is used as its cuprous salt, and the amine in 29 must be acylated to prevent overchlorination. Now we are in this we are going to do the synthesis. From diphenyl we did do the nitration, nitrodiphenyl we did get. By the nitration we do the reduction using palladium charcoal, hydrogen over palladium charcoal in the presence of acetic anhydride. Actually we have do the acylation, reduction and then acylation, because we need protected amino group, otherwise it will interfere in the further reactions. Then we have done the chlorination, and then we have used HCl water. In the presence of HCl water we have done the chlorination, we got 28, and then we have done the diazotization in 28. This is just what are we doing in 28? So if you remember the structure of 28, what was that? 28 was having NH2 group over there with phenyl, but there was a chloro along with that. So we have done what? We have done the chlorination. We have protected amino group, and we have done chlorination of that substrate. After chlorination, after doing chlorination, the chloro will come at ortho position to the amino group. So after chlorination we shall do the diazotization using sodium nitride, HCl, cuprous, cyanide. When we shall do diazotization, there will be N triple bond N. Diazo group will be there, and that will be displaced by the cyanide group. So cyanide group will displace the diazo group. So we shall get 32 at this position. Now from 32 we can get 27. How can we get 27? We just do hydrolysis, we can get carboxylic acid. Hydrolysis of cyanide compounds can give us carboxylic acids. So we can get 27 where their cyano group is converted into the carboxylic acid by simple hydrolysis. If a series of reactions must be carried out, start with one that gives a single product and unambiguously, and no one that would give a mixture of products. If there are a series of reactions, we should prefer the single product one reactions rather than mixture of products. With aromatic compounds, if you need to add both ortho and para substituents, first may be less ambiguous than the reverse. So, the compound 33 was needed to make some antimalarial drugs. This is 33, we needed it for making antimalarial drugs. We prefer not to disconnect the OET group, and there are good reactions, nitration and chloromethylation, that would go to the right position to the activating OET group. So either disconnect A or B could be tried, disconnections A or B could be tried. So we did not disconnect the carbon to oxygen bond of ethoxy because ethoxy is activating. So nitro is deactivating and nitro is meta directing. Here we don't need it. So first of all, disconnect nitro. So that will be synthesized. That will be first disconnection will be added at the last. So first we shall do, we can disconnect A, the nitro 1 disconnection. We can do the disconnection B, where we can do the chloromethylation. In the case of nitro disconnection, we can have 34, in which there is ethoxy and chloromethyl. And in the case of A, the 34 can be made by the chloromethylation of 36. So 36 is there available, for example, commercially available compound. So we can do the chloromethylation of 36, we can get 34, and then we can get back 33 by nitration. The other way, the disconnection B, we can disconnect the nitro group. First in the B disconnection, we first disconnect the chloromethyl group, C2C bond, and then we shall be getting 35, and after that we shall be doing the disconnection of C2, and then that we can get from nitration. So from 36 we can do the nitration, we can come to 35, and from 35 we can do the chloromethylation. So there are two things, both can be done. So what should be done first? Either we should do the nitration first and chloromethylation afterwards. That is also possible. And if we can do chloromethylation first and then nitration, that will be wrong. So we shall be discussing it on the next slide. Now we expect the para product to be the major product from either reaction on either 36 steric hindrance, so it makes sense to the nitration first. There is a danger the nitration of 34 might oxidize CH2Cl group to C double bond OH group or even carboxylic acid group. The synthesis works well if nitration is carried out first. So first we do the nitration and then we do the chloromethylation in the presence of zinc chloride. We can do in the presence of HCl and formaldehyde. It should be obvious that not all of these 6 guidelines will be relevant in every synthesis. Indeed, some may even contradict others. So the way these steps are not exactly the same in all the synthesis. Maybe some different strategies can be used. It's a matter for judgment, and then laboratory trial is to select a good route. As always, several different strategies may be successful.